so going into course content here, went ahead and put a key there. All right, so if you're interested in seeing the key, it is on Blackboard. All right, so here's the key that I used in grading. So what I want to discuss is sort of piece by piece where points are taken off, because this is important, because I don't curve in this class. So I just want to know that we're communicating well. So, and my grading should be a communication to you. So let's go ahead and talk about this one. I was asked to use equation 1.7, so I wrote out equation 1.7. And it states that the dot product can be written as the product of the two first components of the two vectors plus the product of the two second components plus the product of the two third components, which can also be written in this form as a summation. And then there's also something called Einstein notation, where you don't have to write the n equals 1 to whatever. It is just assumed that you're summing over all possible values of the repeated subscript. All right? So it's fine. That'll be the notation I use. So if you want to use that, that's fine too. This is the notation I believe your book uses. Right. So I need to take the dot product of the vector r and the vector which is equal to the resultant of u plus v. That vector is going to have components u1 plus v1 well, in the x hat, u2 plus v2 in the y hat, and u3 plus v3 in the z hat. So I write the first component of r times the first component of u plus v, the vectors, which are the components, the ith component of u plus the ith component of v is the ith component of u plus v. All right, and then I just distributed my r. And then I noticed that this summation gives me 6 terms that I add up. So I've got 3 from here and 3 from here. But I can also break it into 2 sums, where I sum these first 3, and then I sum these second 3, in which case it would be written like so. And when I look at that, I see that it is actually the sum of 2 separate dot products. All right? And that was what I was to demonstrate. Any questions about that? You all got it right? Okay. So the next one, if r and s are vectors that depend on time, prove that the product rule, which is that the time derivative of the dot product, is equal to the time derivative of the first vector dotted with the second vector plus the first vector times the time derivative of the second vector. All right, so I start with the left-hand side of the thing that I am to prove. I notice that it's the time derivative, and I make a substitution from 1.7. Because I'm taking the time derivative of a sum, the time derivative can commute with the summation sign. So I've got the sum of the time derivatives of the product r sub I, s sub I, and then I get to just use my product rule as it pertains to scalar functions. And I do that, I apply that, I get the derivative of the first function times the second plus the first function times the derivative of the second, and I've got my summation. Again, I see I'm going to get 6 terms in this summation, 3 from here and 3 from here, so I can break it into 2 sums of 3 terms, which I do here in the next line. And then I notice that the derivative of vectors, ith component with respect to time, is the derivative of the vectors, I'm trying to say. I guess that's what all I'm trying to say, is that is the ith component of the derivative of the vector with respect to time. All right? So bearing that in mind, I will go ahead and make my next step, and I get the expression that I wanted to prove. All right, so things that happened here. Sometimes we didn't really know where to put our summation sign, what we were summing in the dot product, how to apply 1.7 correctly. That was a couple points off. Another thing was that sometimes we didn't know that the time derivative is indeed an operator and it has to appear in front of, meaning to the left of whatever it is operating on. That is the only place where it has mathematical meaning. So again, that's a couple of points off. And another error would be to not notice or to not communicate to me when things are scalars and when they are multidimensional vectors. And so that was also 2 points off, right? Okay, are there any questions at this time about that? All right. All right, let's move on to the next one. I don't know why the copy machine did not scan this page very well, but hopefully you can see it. Oh, another thing to notice on that first one. If you didn't write out the statement of the questions, you lost 3 points each time. All right, so number 10. So here again, I needed to write out the statement of the question completely. You can paraphrase, but it still had to contain the complete question with all needed information. That's going to be 3 points. So a particle moves in a circle at the origin, radius r, with constant angular velocity omega in the counterclockwise direction. The circle lies in the xy plane, and the particle is on the x-axis when t equals 0. Show that the r vector is equal to x hat r cosine omega t plus y hat r sine omega t. That, and B, find velocity and acceleration. C, what are the magnitude and direction of the acceleration? And D, relate the results to properties of uniform circular motion. I broke it out into 4 parts. Your author, remind myself of what the statement of this question was. And this was kind of a tricky one because getting all of the questions answered was the most, or not doing that was the most common error. So let's take a look at the question as your author states it. Is that a minus or a plus? All right. A particle moves in a circle, center O, radius r, with constant angular velocity omega. Counterclockwise, circle lies in the xy plane. The particle is on the x-axis and t equals 0. Show the particle's position is given by. Find the particle's velocity and acceleration. What are the magnitude and direction of the acceleration? Relate your results to well-known properties of uniform circular motion. So that's the way that the author stated it. I just break it up into 4 parts. Oh, I've already got those on the other thing. Here we go. All right. Okay, so for part A, I went ahead and wrote the expression, I went ahead and drew the vector for the location of the particle at some time, t, in which case the angle relative to the x-axis would be omega t plus whatever it was initially, which was 0, because it was initially at the x-axis. All right, so then I noticed that the x component of that location, if I want to write it in rectangular coordinates, the x component is our cosine phi, where phi is omega t, and the y component is our sine phi, where phi is omega t. And so I went ahead and wrote that here and made the substitution of omega t wherever I saw phi, and I was done. All right, for part B, to write the velocity vector. Now that I know the r vector, I just take the time derivative of it. So for the first term, I get x hat times the time derivative of this guy here, which is, well, r is a constant, so it pulls out front. Derivative of cosine omega t is negative sine omega t times quantity times omega, just by chain rule. And then plus the time derivative of the second term, which is y hat. Again, r is a constant, so times cosine omega t, because that's the derivative of sine omega t, and then omega by the chain rule. Okay? All right. So now I have my expression. And then I also went ahead, just being a goody two-shoes, and looked back in my notes and noticed that r sine phi and the minus x hat and r plus r cosine phi and the positive y hat was what we had found would be the phi hat direction. So I noticed that this was equal to omega r in the phi hat direction. All right, acceleration. Again, I took another time derivative of velocity. And so this is really just math. I add this expression here, which simplified to minus x hat times omega squared r cosine omega t minus y hat omega squared r sine omega t. But remembering that x hat r cosine omega t plus y hat r sine omega t was the r hat direction, what I see is that I get, I'm sorry, I should just say was the r vector, then x hat cosine omega t plus y hat sine omega t would be the r hat direction. So I can rewrite this as omega squared r in the negative r hat direction. All right, so done with that. What are magnitude and direction of acceleration? I've already noted that the magnitude is omega r squared. That should be omega squared r, sorry. minus 1. And the direction was negative r hat. And, okay, so I really should fix that. Give me just a minute. I'll fix it on the scan as well. And what I notice is that uniform circular motion, things I knew about the uniform circular motion was that the speed, which is always the velocity is always directed in tangent to the circle, and that the magnitude of that velocity, also known as the speed, has a value of r radius times omega. Also, uniform circular motion, something I knew about it was that the acceleration would be toward the center and have a magnitude of v squared over r. Plugging in r omega for v, I see that that is equal to r omega squared. Again, it's toward the center of the circle, so that should be in the minus r hat direction. So yes, this all agrees with what I already knew about uniform circular motion, which was those two things. Are there any questions about it? All right, so in terms of the rubric, so what does that say? If you only did part A, obviously you missed a lot of points. And that'll be a tough thing because you always need to read the question completely. Don't just ask the first thing that is, answer the first thing that is asked, because there'll be a lot of compound questions. Another thing would be if you, expressed the r vector as the magnitude of the r vector. Again, those are different things. We need to remember that this symbol does not represent a vector. This symbol does represent the magnitude of a vector, but those qualities don't hold to that magnitude. So, all right. Okay. All right. And I'd say the biggest mistake was not answering part C for some reason, expressing acceleration in terms of magnitude and direction. So, but I get that. And that's part of why we're going to work in, why I'm going to ask you to work in groups. Because one person can forget part C, but it seems highly unlikely in a group of 3 people that everyone would forget part C. So as we're working in groups, we want to make sure that we are working somewhat individually, but also touching base with each other to make sure that we're all getting it done well. All right. So that means that it should, what I mean to say there is that in those groups, even though I said it's okay to look at somebody else's paper, if everybody who's working on this problem is like, hey, let me see what you did, and they all look at the same person's paper before they begin, then that is going to propagate those errors. So you should at least make sure that there's some diversity of work in that group. All right. All right, so let's move on. Number 18. The 3 vectors A, B, and C are the 3 sides of a triangle, ABC with angles alpha, beta, gamma. Prove that the area of the triangle is 1/2 A cross, 1/2 times the magnitude of A cross B, which is equal to 1/2 times the magnitude of B cross C, which is 1/2 times the magnitude of C cross A. And B, use this equality to prove the law of sines, which states this. All right, so for part A, I just sort of went about it. So I'm thinking about the magnitude of A cross B. Now, the magnitude of A cross B is, some of you proved this by noting that it is equal to the parallelogram who has 2 sides that are equal to A vector and 2 sides that are equal to B vector, and that this triangle is half of that parallelogram. So that would be a fine thing to do. But I'm going to use the area of a triangle is 1/2 times the height of the triangle times the base times the height. So in this case, for A cross B, I'm going to choose A to be my base, and then my component of B that is perpendicular to the line of A would be my height. So I kind of have to extend it because of the shape of this triangle, and I get this line here that's perpendicular to the vector A. And I notice that that line is the opposite side of a right triangle, whose opposite side is B, and whose angle opposite to that side is gamma. So that would be equal to B times the sine of gamma, which I went ahead and plugged in there. All right. Same thing was done here. I'm going to treat B as base. Then that should be times the height, which in this case is C times the sine of alpha. That'll give me this dotted line here. And I didn't repeat it in terms of drawing for the next one. Now, if you did it for the first one, and then you wanted to say, well, it must be the same for all of them, that is fine. But you have to say it must be the same for all of them, and you have to give me the reason why it must be the same for all of them. And the reason would be because without loss of generality, I could rotate this triangle and rename these sides, correct? Right. But you can't just say and, you know, it's equal to this, and it's equal to this, without communicating. So this is really, remember that your homework is a communication. And yes, we all know it's true. It's a homework question just to prove it. But you have to do the proof, which means it has to be mathematically complete. All right, so just communicate the lines that without lack of generality, I could rename the other sides of this triangle, or rotate this triangle, or whatever you needed to say. All right, you do have to say it. You can't say, I have therefore proven that this is true and this is true as well. Okay? All right, so then when I wrote an expression for area, I got the expression I wanted. A very common mistake on this was to not write the statement of the question. And again, another common mistake was to say that it holds true for the second two cases without any reasoning, without a reason or a statement, which would be perfectly adequate, a reason or a statement. Even the first argument by saying this area of this triangle is half the area of the parallelogram, and I know a cross product gives me the area of that parallelogram, that would have been a fine product. That would have been probably the easiest proof. So that would have been fine too. There's more than one way to skin a cat here. All right. Use this equality to prove the law of sines. Okay, so I already know this. So I just plugged in wherever I see the magnitude of the cross product, AB times the sine of the angle between them. And so that is what I substitute in there. And then I divided by ABC, and I wound up with the expression that I needed. All right. Okay. So let's just go ahead. Are there any questions about that? I actually flipped it over and then divided by ABC. Is that all right? Okay. Oh, errors on that one. Let me see if... Errors on that one were to, again, prove it for two of them, but to make no statement about the third in terms of reasoning why the third equality must hold. Again, it doesn't take much to say without lack of generality, it must hold for the third as well. That would be fine, but you can't just state that it is there without a reason. And proofs are proofs. You know how they are. All right. 30. All right. Conservation laws often give a surprising amount of information. All right, you didn't even have to write that if you didn't want to. That's not a part of the statement of the question. It's just an opinion, which is fine. Two objects, M1 and M2, are subject to no external forces. M1 is traveling with velocity v when it collides with M2, which is at rest. The two objects stick together and move off with a common velocity, v prime. Use the conservation momentum to find velocity in terms of M1, M2, and v. And so obviously I'm trying to, again, give you a problem here that will be very much about form in terms of doing the homework so that we can sort of get through my expectations. I went ahead and drew a figure here, and I didn't make a coordinate system because I'm not going to use one, so that's fine. And then I wrote the impulse momentum theorem. That's the more general statement than the conservation of motion. And conservation momentum, sorry. And I see that the impulse is equal to the integral of force dt, and by the way, that force has a vector sign on top of it, from t initial to t final. This is equal to 0 for two separate reasons. So if either of these were true, it would be equal to 0, but both of them are true. We've already been informed that that there are no external forces. So the net external force is 0, so because this guy here in the integral, the argument of the integral is 0, therefore the integral is equal to 0. I've also heard the word collide. And collide is a physics code word for something that takes a zero amount of time. A collision and an explosion always are approximated as taking zero amount of time. So even if there had been an external force, the impulse still would have been 0 because I would have been integrating from t initial to t final, where there is 0 time between t initial and t final. So from t initial basically to t initial. So because of these two, this taking 0 time, the area under the curve from t initial to t final is 0 as well. All right? So not only is this a rectangle with height of 0, it is also a rectangle with width of 0, is what your author has told you. Okay, that's fine. 0, we get it. All right, so in that case, we have conservation momentum, which I just went ahead and wrote as final momentum equals initial momentum. Some people wrote it in a way that agreed with their figure, which seems clever. All right, I plugged in for final momentum. They're both moving at the same velocity. Initially, one's moving at velocity 0, one's moving at velocity v1, and I solved for v prime. All right, so that's fine. So again, though, this gets to form. So a couple of things. One is I didn't take off for the lack of the vector this time. It was the 4th time with the same mistake, and I just got tired of taking points off. But again, this thing here, in theory, I should have taken a point off by it. Also, this problem, the reason I wanted to do this problem was because I wanted to illustrate that you, as a physicist, which I believe you are, need to state the statement of the law or definition or physics idea that you are applying with its name. All right? After which you can apply it to your specific situation. So if you had started with just this line down here, without this line, hey, I'm going to use conservation of momentum, which I know generally says this and specifically gives me this, then you lost points. All right. If you didn't lose points, yeah, you did lose points. So basically, whenever you use a physics law or definition, you're going to have to state that you have used it. This is, again, about communication. And it's not just with me, it's also with yourself. When you go back and look at these notes before you take your qualifier, it's about that. But it's always expected. When you're in a research group, it's expected. At every step in your life from here on out, that's the expected form of communication, and that's what we're going to do. As a result, whenever you're using a physics or law or definition, you have to do that. You pretty much always have to do that for your first step, because I assume you're always going to start with a physics idea. Maybe if you're starting with a statement of 2 + 2 = 4, then you don't have to name it, but pretty much almost always you have to name your first line and write it in its general form, or you will get 2 points off. All right. Now this next one is about figure drawing and free body diagrams. So very, very tactical about this assignment, basically because I wanted, if you're going to step into cow pie, I want you to do it here where we can drop the score. So again, I needed a statement of the question. A student kicks a frictionless puck with initial speed v0 so that it slides up a plane inclined at the angle theta above horizontal. So I just use this little symbol here for angle, just if you're wondering what that is. Write Newton's second for the puck and solve it for location as a function of time. How long will the puck take to return to its starting point? Those are the questions. All right. The thing that I had to do was I had to draw a figure. Why did I have to draw a figure? Because I'm using a coordinate system in this problem, and I have to label the coordinate system. Therefore, there must exist a figure in which I define that coordinate system. All right? The next thing I have to do, because it is a Newton's second law problem, is I have to draw a free body diagram. Because it is that diagram that is going to be expressed in symbols in Newton's second law. So you might say, oh, in this class, a free body diagram, when you're applying Newton's second law, is an absolute requirement for full credit. All right? Again, the reason for that is that it allows anyone reading your next statement of Newton's second law to understand where the terms are coming from. Each of these arrows is going to have an x component that'll appear in this sum and a y component that'll appear in this sum. It's just so that one can follow. We're not going to skip that step, okay? All right, so I wrote Newton's second law for the x direction and the y direction and the z direction. The y direction is not completely trivial, although all I needed to find was y as a function of location, because I'm just finding location as a function of time. So I already knew that by my choice of coordinate system, my y component of acceleration would be 0, because this puck is on a solid surface, therefore it will not sink in or jump out. It will do so negligibly. And therefore the y component of acceleration was 0, and because the initial y component of velocity is 0, meaning it's not sinking or jumping out, then its location will be initially 0 and will continue to be 0. All right? Now the z direction, Newton's second law, was very, very trivial. It just gave me z dot dot is equal to, there's nothing on the other side of equality at all. And for the same reasons, z must remain 0. All right, so the only thing that's interesting here is the x direction. So for Newton's second law, I plugged in on the left-hand side all x components of all forces. Using this coordinate system, I noticed that the x component of the normal force is 0, so that's why it's not there, although you could write a 0 there if you wanted to. And the x component of the weight is negative mg sine theta, and that would be equal to m times the x component of acceleration, or x double dot. All right, so now I get x double dot all alone on one side of the equal sign, which gives me negative g sine theta. And then I integrate from 0 to t dt on both sides of the equal sign. My equality will still hold in that case because I'm doing the same operation to both sides. And I get that velocity is a function of time minus initial velocity is equal to negative gt sine theta. And then I again integrate that. And I get x as a function of time minus x naught. I'm going to make my coordinate system such that x naught is 0, which I write right here. I'm going to choose coordinate system such that x equals 0 and t equals 0. Must be equal to v naught t minus 1/2 gt squared sine theta. And I get this expression. And then I also write, since I was asked to find location as a function of time, location is a vector quantity, so I write it as a vector. All right. So the most common error here was to not follow the instructions statement of the question, which was to write Newton's second and solve it for location as a function of time, not to write a kinematic equation and say that's the solution. We were asked very specifically here to start for a certain starting point and a means to the answer. But of course, this is a kinematic equation. All right. And I don't know why the I is there, but it should say it returns when x equals 0 again. So x as a function of time is 0 is equal to that. I can divide by t. Some people did it as a quadratic, which is fine as well, but you can just divide by t and solve it as one equation, one unknown. Why do I keep moving it there and then it covers up my answer? Go away. All right, anyway, so the final answer is t is 2v naught over g sine theta. And again, the most common errors here were to, really the most common error was to just start with the kinematic equation instead of following the instructions. But the thing that I wanted as an error, if it was going to happen, was to have a lack of a figure, because then you have not defined a coordinate system if you have not drawn a figure, and therefore there's no way to write this in terms of coordinates, or a lack of a free body diagram, which is the step between the figure and substitute and applying Newton's second law to your specific situation. All right, so that hurt. That definitely hurt. But hopefully you're sort of, you know that the point of this was just an exercise to be very clear about the expectations of the homework assignments. And again, because it is sort of a learning exercise, you can decide between now and whenever I submit grades at the end of class whether you want that grade to be a part of your grade. Okay, so are there any questions about the homework? All right, you will get 50 next time. Let me assign the next homework assignment. I'll just do it right here, week by week. I didn't even add the first assignment. Let's add that. What was it? It was chapter 1, problems 8, 10, 18, 30, and 37. All right, so we will make a new item for homework 2. And it is chapter 1, problem 50. This is going to be one that you have to use MathCAD to solve. This is our first one that is not analytically soluble, so we're going to solve it numerically. Does anybody here not have MathCAD right now? Okay, so I will submit your name to IT. All right. And chapter to problems 7, 9, 11, and 27. And these first couple are very mathematical, and I hope that you find them illuminating because there's a couple of math ideas that I didn't exactly want to lecture. So I'm going to sort of let you work individually on that, although if you have questions, you can always ask me. All right. And I'm sort of doing that, again, pedagogically. Oh, I should write when they're due. Due Monday, 9/19. At 1 p.m. All right. All right. So, and again, you're going to say there's a couple things here that I didn't introduce in terms of the math. No, I wanted you to have an opportunity to struggle with them first, and then I'll introduce them. All right. So, are there any questions about the homework? The only one that requires MathCAD is the first. All right. Then let's get back to this. All right. So, last time we were solving the motion of an object that is moving in 2 dimensions under the effect of gravity and drag. And I asked you to solve the y component of the motion because I had already solved the x component of the motion. And I also told you that we would do that at the start of this time. So, and I will show you the solution, but first I am going to break you into groups. The 3 groups will be Rodney, Sam, Darcy, and Ryan. The second group will be Phil, Jeremiah, and Logan. And the third group will be Cash, Grant, and Dakota. You are going to form into these groups at this time, pick a spot, and you are going to solve it if you haven't solved it, and you're going to discuss it with anyone in your group who hasn't solved it completely, how you solved it. Do you remember your group? Oh, John wasn't in a group? Oh, I'm sorry, you're not on my roster. John, will you join the group where you belong, which is with Cash, Grant, and Dakota? That was just alphabetical, if you're wondering how I did it.
We were on Friday. It's essentially the same thing. You just changed the
Everyone will have the solution on their page in their own handwriting. It's not good enough for the group to have one solution. Everyone needs the solution. Is there anybody who had the solution complete coming in here? Okay, if that's the case, turn over your page as though you never saw it and solve it again fresh after you're done talking it through. All right? That should just take you a couple minutes if you've already done it. And I'll put up the question again. Get my notes from last time.
Instead of the whole
So we got linear drag. Right, the x component has already been solved. We are solving the y component, and this is what we got out of Newton's second law. We're solving it. If once you've had a chance to talk it through with your group partners, if you'd already solved it, take a fresh page and resolve it.
That makes sense.
this coordinate system is going in the negative direction. Oh, it's opposed. Yeah, which is, yeah, so, okay, like, okay, so if you have, okay, so this is the, okay, so that's the particle in motion, okay? That's it in motion, right? That's the velocity. Yeah, okay, yeah. So this is the drag, okay? That's going in the opposite direction, because this V line has a positive y component, you see that? Because it's going upward in the y direction, so its drag is going to oppose that, it's going to be negative. You see that?
Say the particle's going straight down, right? It's still going to have negative weight, but in this case,
Yeah, but this particle's not going straight down. Yeah,
just this part.
Yeah, just this particle, yeah, depends on however.
You can't take it out of context.
Yeah, like how she solved it originally.
That's right.
Yeah, it was going straight there. Yeah, just not this one.
The first step, take some of the forces that you are from those we have more that's and that is just obviously just yeah, that's right. Same, yeah, just the same idea, but it's just something
Couldn't be A or the natural two variables.
yeah. And to solve your initial or boundary condition, not initial condition. That makes sense. Yeah.
Yes, sir.
When I did this,
Yeah.
I did some of the forces into my thinking because
Yes.
in one dimensional
Yeah.
you have empty.
Very correct. And in here, I've labeled my coordinate system where y hat is down. And in this figure, I've labeled my coordinate system y is up. And this is more general. But anyway, yeah. And that's why we made V, for right now, V naught to be positive x, positive y components, because that will still,
Okay.
without lack of generality, apply even if those are negative numbers. So we'll be, this is
I
sort
see
of
that.
us just getting going with it. The more general solution is the one we're getting at.
I see that. I didn't even pay attention to that. Y hat is down. Still in effect.
That's how it is, I know, yes. Details. All right. So we have an issue. So here's your solution. But we changed, oh, this is x. I need to be, I'm sorry, that makes sense. We changed variables. We're going to change variables here so that we can have the same variable here as we have here. So that's the step where you are. Did you guys do a change of variables to vy minus v term, or vy plus v term in this case?
Okay.
I'm just
So you're getting there?
V term is,
MG over v?
yeah, well, it's
Yes. And you wouldn't have to call it that, but you are going to have to change your variables so that this guy is the derivative of the function over here. So let me go ahead and pick it up from there. All right. So I'm going to go ahead and get started. And I'm going to do this thing for speed, which is not a bad thing to do because this class will have in-class exams, so we do have to be able to do these things. That's why I had the people who'd already done it flip over, do it fresh, because this is the sort of thing that's like a skill. You know, you can learn a soccer move, and you can do it while you're thinking about it's really slow. You won't be able to use it in a game until you get to the point where you can do it with your eyes closed. All right, so same sort of thing is what we're going for here, and I call that being facile. Meaning that you can do it without thinking too long about it, meaning that you can do it at the pace that you need to get a problem done on an exam. All right, so in this case, I'm asking you guys to solve the y part of the problem. So I've gone ahead and drawn the system here. I went ahead and had the object moving initially in the first, that vector's in the first quadrant. But if any of those components were negative numbers, these final solutions will still hold because that is general. That is very general. I've done this in the most general fashion. All right. So I'm going to go ahead and start from this line, if that's okay with you guys. Do you want to turn off that light again, Darcy? Both, all of them. So are you guys okay with this line? Okay, so MA, I've got for my y component, I've got a negative mg of this guy, and I've got negative b times the y component of v for that guy. All right, so let's go ahead and do the math. Mvy dot is equal to minus bvy minus mg. All right, and I am going to pull a negative b out front, and that gives me vy plus mg over b in my parentheses there. Now last time we found that mg over b has its own name. It's called the terminal velocity. All right, so what I have here is minus b times vy plus v term is equal to m times vy dot. All right, so next thing I'm going to do is I'm going to divide both sides by m. Boom. And then I'm going to say, you know what? If this vy plus v term were my variable, then its derivative with respect to time would just be equal to vy dot dvy dt time, because terminal velocity is a constant. So I can write vy dot as vy plus v term quantities time derivative. I'm just going to write it with a dot anyway. Hopefully that makes sense to you. But that dot is over everything inside these parentheses. Great. So now I can look at this and say I know what vy plus v term as a function must be equal to some constant times e to the minus b over m times time plus a second constant. That's when I see a derivative like this, the only function that does it is the e to the this thing times time. So vy plus v term is equal to a e to the minus b over mt plus b. Vy is equal to negative v term plus a e to the minus b over mt plus b. Now I need to figure out what a and b are, and I do that with boundary conditions. So I'm going to go ahead and apply some boundary conditions. One boundary condition I know is that Vy, as t goes to infinity, will be equal to negative v term. It'll be moving downward at its terminal velocity. So that tells me, well, when t is infinity, this term will be 0. I've got negative v term plus this term, which would be 0 in that limit, plus b, and b must be 0 for that boundary condition to hold. Another boundary condition is Vy when t is equal to 0, I should say this, t equals 0, must be equal to v naught's y component. All right, so that means that 0 is equal to minus v term plus a times e to the 0. That's not correct. Why did I plug in 0? That should be Vy naught. V naught y. The value at t equals 0 on the left-hand side is equal to the value at t equals 0 on the right-hand side. So I know that a must be equal to v naught y plus v term. I'm going to plug that in. I'm going to keep you guys for an extra minute. I get minus v term plus v naught y plus v term e to the minus b over mt. And that's Vy as a function of time. Now, if I want to get y as a function of time, I need to integrate both sides from 0 to t. And do the same thing over here. Integrate dt 0 to t. All right, and I get y as a function of time, minus y naught, which I can go ahead and choose coordinate system, so that's 0, which is fine. And that gives me minus v term times t integrated from 0 to t, also known as t. Now I have to think about this integral. V naught y plus v term, I'll pull that out front, times the integral e to the minus b over mt dt. Now in order to make this Jacobian right, I need this to be times negative b over m. And in order to do that, I have to multiply out front by negative b, m over b. All right, so I've got minus v term t plus, I'm going with m over b, v naught y plus v term. And you might be saying, where's your minus sign? Yeah, I know, I'm going to do that. Integrating this from 0 to t, it's going to give me e to the t minus e to the 0, which will be 1. And instead, I'm going to write the bottom term first. So 1 minus e to the minus b over mt. All right. So that's a super messy solution, but that indeed is y as a function of time. I would like for you guys to go home, turn the fresh page, and get that answer for you in 5 minutes. Well, it took me 5. So for you in 10 minutes, given that you started from here. Just be able to do that type of math in 10 minutes. We'll see you next time. It takes practice. So don't be frustrated if you can't do it. Of course you can. Until you practice it, nobody can.